We were doing the distillation column. And we had defined the system, talked about why it was a good neural net application. And so we're going to move forward. We're going to define the state variable. It defines the variables that we can actually measure and use in our controller and our supercomputer. So in this chemical system, you can't observe all of the variables. In other words, you can't put sensors all throughout the column and observe everything. In fact, even just measuring the composition of what's going in and what's coming out is not easy because you have to do chemical tests on it. And so the observables variables that were used here are the flow rate, F, temperature, T, and the chemical composition. This is listed as X1, X2, and X3, and this is percent concentrations by mass. Of the three chemical compounds. And let's see, X1 is the heavy component. X2 is the middle. X3 is the light. And by heavy, middle, and light, heavy means it has a high boiling point. And the light means it vaporizes easy, so it has a low. It easily boils, so it has a low boiling point. And then we measure these at places where they can be observed. And so this is done at top, that's in the hold-up tank, that tank at the top. The bottom, which is the boiler. That's and then the side stream. Stream coming out the side of the boiler. And those are places that this stuff can be measured. So the state variable, the collection of variables that were used to describe the system, temperature, feed rate, X1, X2, X3 at the top. Temperature, the feed rate, body. And then the temperature, X1, X2, X3. No feed rate there because you're not feeding. No flow rate, it's just coming out. We didn't measure that. That's the side. So those variables have 3 different locations. Then the control variables are the heat in the boiler, the temperature at the condenser, and the speed rate. That is, how fast are they feeding it in with the side? Not taking it out, feeding it in. So first thing I'm going to do is a neural net model of the system. I'll show you what we do there. So this thing takes the state vector times t, and then the state vector 1 times step 4, and then the boiler heat. This goes up, this goes up. Current heat, current condenser temperature, and then the speed rate. All this condenser. And then it's going to output the state at the next time step. So based on when we did system modeling, we found out the first order differential equation needed 1 fast time step because, like the dy by 3t, you approximate that as y t plus 1 minus y t over delta t based on first order, which is 1 derivative. And so you can predict the next time step based on the current time step plus whatever inputs are coming into the system. So we look at this, and they're using 2 past time steps, the current and the past. And so that means that the model here is assuming a second order system. Since there is no real good math model for this, it's easily just written out as a differential equation, they are making an assumption here. And so it'd be entirely possible that if you were doing this yourself, you might want to try another past time step to see if that made it better. All right, so this thing had 14 linear inputs. – 157 sigmoid hidden neurons. In 2 layers. And then just the number of outputs is whatever matches the state variable. So 14 linear output neurons. So let's draw a rough picture of the distillation model again. remember the column is this thing with all the plates. This. Right, and so we're saying the state vector, we can measure the state top. We can measure, sorry, not the state, it's the T, X is X vector up here. Down to the bottom, we can measure T, and X, and then we measure what's coming out the side, T and X, right? So we said we can't measure everything going on inside. So the question is, and maybe hypothetically, the variables that are going on inside are modeled by the activation functions in some general fashion of the hidden neuron. Because this thing is representing the states that we can observe, and then what are the states that we can observe coming out. And so that mapping has to somehow take into account the dynamics of the values in here. Now you can't go in there and say, well, this neuron is the composition X1 at this plate here. But inside the neural net, there is some modeling going on. And if for some reason we did have a really big fancy equation model for this, we could throw that equation model in there and actually learn the model. If you know, remember the, let's see, which, oh, it's a rotary robot arm, right? We said if you know what the activation functions look like, their sines and cosines, stick those in as neurons. And it will figure out how to use those equations to actually fit the model, the math model. So if you had a good math model here, you could tailor the network to fit the math model that's in here and then learn the parameters in it. But we're going to do this more general. We're just saying, okay, we have a neural net and we're going to do this. But understand that the information inside the neural net has got to map the information that's going on inside the column in some way. All right, so we have the architecture for the neural net. We have the system that we're trying to model. The next step is, well, how do you get training data? Because we need data to do that. And so collect training data. And like any system, including the truck, essentially we drive it around and collect data. So for the truck, we drive it around backwards, varying the steering wheel angle and seeing where it goes. Same deal here. So we're going to drive the column around. We'll put driving in quotes because we're not actually loading it up in the back of the pickup truck and driving it around, right? So the startup, that's where they turn the boiler on and get things going to steady state, where it's operating in a steady state manner. This was 20 minutes of that happening, and it was sampled every minute. And then after steady state, this is where they drove it around. They varied the feed rate, and the boiler heat. Denser temperature, so those are the control variables. Sinusoidally, about steady state. For 135 minutes. Here's one of the results. Let me put that up on the screen. You can see that here. Let's share it. So this is the heavy component X1 and the light component X3 from startup to steady state, and then you can see the oscillations due to varying inputs. And this is after it was trained. And the predicted and the correct is the more solid line. The predicted, you can see that it's pretty much right on top of it. So there's a little bit of variation up here, but it did a good job of learning how to model the system. So that's the model.
And so that's after they trained it?
After training, yeah. Because before training, it wouldn't even be close. Yeah. Okay, so then the next thing to do is how do you use the model for the controller? Here's the control goals for the whole thing. So many variables, you have to decide, well, what do you want to track in this thing? And so here's the goals. They're pretty simple. First thing is to reduce concentration of the light component. So this is the one with the low boiling point. Light component in the bottoms. So rather than trying to drive the heavy component bigger in the bottoms, you're just saying, let's get rid of as much light component as we can in the bottom. And the same thing at the top. So reduce concentration of the heavy component in the top. Because you want mostly light up there, so let's get rid of all the heavy. So if you're doing the alcohol thing, the alcohol tends to boil at a lower temperature than the water. And so you'd want to reduce the amount of that in the bottom and reduce the water in the top. Better concentration. And training was done two different ways. The first way was just like the truck backer upper extent. Here we have access to values at all times rather than just when it hits the dock. And so we can backprop through the model at every time step. And then the second method is something that I want to show you. We know how to do inverse control, and we know how to do the backprop through the model. This is pseudo or partial inverse control. And when you first look at it, you'll say, what the heck? And then you'll realize it makes total sense. I hope. I need to draw the controller up here so that we can talk through that. All right, so here's the whole system, a big block diagram now that we've talked about the model. Here is the distillation column. Here is that model that we've already done as a neural net. So this is our ANN model. And both of these put out the state vector in the next time step. The model just does it because that's what it does. And then, the column does it because that's just what it does, and the model puts out an approximation depending on how well it learned. And the distillation column just takes in that control vector, which is the heat, the temperature, and then the feed. And of course, the model takes that in as well, but it also needs the states now and one time step before. Then the controller, its job is to figure out, well, what inputs, what heat, what cooling needs to go into the system to get what we want out the other side. And so it's going to take some kind of reference input, which is what we defined over here. Our reference input is the light component, which is x3 at the bottom. And the heavy component at the top is x1 at the top. So those are the only variables that we're going to reference here. Is this going to be the vector? It's x3 at the bottom, because we want to try to reduce that, and x1 at the top. So that's what we want to track. We're going to try to force just those elements inside this big state vector. Only those two elements are going to drive. And then, of course, this is going to take the current and the past state information, the same thing that went into the block. So for the training option number one, we simply do what we've always done. The model is trained, just like we did for the track backer upper, and then we compare the actual value, the x3 at the bottom, with the reference then x1 at the top, with the reference value. And that's our error. I guess I flipped those around. You can flip them around again. That's the error. You backprop through the model, and you train the controller. And you can see why here we can do it at every time step, because we have a reference value at every time step. Whereas for the truck backer upper, we didn't have where we wanted the truck to be until we hit the dock. So that's why we only had a reference at the end of the time. And that's why we had to do all that back prop through time.
Interesting. You said, I don't know if I might have misheard. You said the, for both the control and you said the previous time step, but then you said S of t plus 1.
Oh, that's wrong.
Okay, that's not.
You're confused because it's not right.
I thought it was.
Yeah, sorry. Are these things in your way? Anybody?
There's just a little, I can see it.
Which one's mostly in your way?
No, right,
This one?
yeah.
Better? Yeah. Yeah.
What's the S hat t plus 1?
Which one?
That's
the neural network one.
Yeah.
That's the neural net. That's like the neural net.
Here? What about it?
Like, what's the difference between that and the upper column? Because
The difference between this and that?
yeah, but will it be the same? Like,
Well, if we train the model really well, they're going to be close. As you've learned when you train a neural net, you don't get exactly the right answer. So like if we train an RMS of like 0.1%, then the difference between these two on average is going to be that 0.1%.
Where would you be getting those reference values?
We make them up ourselves. And I'll show you those. What's done is it starts out at the steady state and then it stair steps down to try to reduce it. But yeah, you have to provide these. So if you had a target X1 you wanted, that would be your reference. All right, so then the other thing I would show you is I need to show you what the controller looks like. It's pretty much like the model. It's got hidden neurons and all that. But this partial or pseudo inverse control. Yeah, we can use this here. Now we're focusing on this training method. So let's go back and remember inverse control. If we have a system like that two-link robot arm, we put in theta 1, theta 2, and we get out x2 and y2, right? That's the system. So if we put in a theta of 25 degrees and 45 degrees for this, and we get out a position of 3.5 and 1.2, if we want to put the arm at 3.5, 1.2, this is what we want to use, right? And so that becomes the training for the inverse control. So you run the system, collect a whole bunch of data, look it around, train the inverse you get. Notice with this, you have inputs but no current states going through. So we just put everything. A partial or pseudo inverse control, we'd be doing the same thing here, except we don't flip the states. We flip the reference values out of here and the outputs. So, for example, let's get rid of that. We put, forget this controller, we put a value of the input into the system and the model, or the system, right? Forget the model. We put those values in here, and it jumps to the next state. Those values that we put in for the control, we know will give us that next state. So if we just flip the control and the next state, that matches what we need here. You see that? Because both of these have this going in. So you don't flip all the inputs and the outputs, you simply flip the control and then the states. Here, in fact, you don't flip all of them, you only do the ones that we care about. And it's the same philosophy, is if we put in a certain control value of 10 here, and we get a 4 here for one of the states, if we put in the reference of the 4, then what's the control value? It's the 10. If we're at this particular state. And so that's what's slightly different, is you're only inverting the reference values here that are inside the state and the control, and you flip it around, and it exactly matches what you need. So that's what you got out of the system. So you can still run the system, collect a whole bunch of data, and then you just flip what you need to match the controller, and you can train that. And so both of these methods were used in this paper. And we'll go through that again, because this is a methodology you use on a project near the end of the semester. I'll talk through that again at that time. Let's see, the controller, again, looks a lot like the model. We have the two reference values, so this is the reference light component at the bottom. is the reference heavy component top. And these are desired, so they're going to be at T+1. Because that's where we want it to be at the next time step. And then we're going to send in the state vector where it is and where it was before. And then we hope that when we calculate U, and it goes into the system, that we get the state at the next time step that matches these two. So there's 30 linear inputs, 157 signaling, and there's only 2 output neurons. Because what this thing controls is just a subset of the control variables. It controls the heat and the temperature. And so it's a constant feed rate. So the feed rate that's going into the model is set to be a constant. And then they attempt to change the temperature and the heat to get their desired output. So I'm pulling up here, make sure I got the right plot. Here's the controller after training, how well it tracked a stair step. So let me get that brought up on the screen. Yeah, so this is the heavy component, X1 at the top. And its after startup has already happened. So its startup has happened, it's come down, and then this is the commanded value of X1. And then the dotted line is what the system actually did. So we're looking at how well did the controller make it do what we were asking. So it hit pretty well this, it's drifting down, and then it steps down to see, let's reduce some of the heavy, and notice that it responds, comes down pretty well, step down again, and responds. So the controller has learned to control the heavy components at the top. It's not an exhaustive evaluation, but it looked like it worked pretty well. And then the next page here is the light component at the bottom. So squint your eyes and look carefully at that. So the solid line is what we're asking for. The dotted line is what actually happened. Looks like it was able to grab that first stair step. But then as it stepped down and stepped down, there's really not much change, is there? So it can control the heavy component at the top, but not the light component at the bottom. Unless you look at it really closely, and you look at the value here, 0.05, where was on the other one? That's much larger, wasn't it? Like 0.1. So when there was a significant amount of heavy component at the top, it was able to reduce it. But it looks like from on startup, this actually did a pretty good job of getting the light component out of the bottom, even just starting out. So I think that's why I wasn't able to control it as well. All right, so the 3 basic questions for this application. Have I told you the answers? Do you remember the questions? These are the questions that if we're in Untitled and across for the Holy Grail, when the guys get ready to cross the bridge, these are the questions I'll ask you to see about when we cross the bridge. You guys watch that movie? It's not one of my favorite movies. There's just parts in it that are funny to me. And there's a lot of scenes. It's a classic movie. Everybody quotes it. So what are the three questions? So it's number one.
Let's see the application.
Yep. So I did that. Right. We spent a lot of time talking about distilling, and I told you everything I know about distillation columns. If you want to know more, you'll have to go to KU or K-State and get a degree in chemical engineering, because we don't have one here. Although we're starting one. Plans. Driven mostly by Koch Industries, so of course they want chemical engineers, and they want some of their engineers to be able to do chemical engineering. I don't know where that is. I think it got approved, but there wasn't any money available. That's a real driver for anything. But I think it's still in the works. Okay, so the application, you guys got it, right? Nobody in here is a chemical engineer. Otherwise, you should have been teaching this. What's the next question?
The architecture.
The architecture for the controller, right, and how it's trained. So I showed you that. In fact, I showed you that it could be trained two different ways, right? Either backprop to the model, which means it's that neural model adaptive control, or we did the pseudo or partial index control. And question number 3.
It's why.
Oh, wait a minute, back up. There's actually question 2B, part B, is how do you collect data to train? And we talked through that as well, right? So what's the architecture, how do you train, and then how do you get the data to train? And then question 3.
Why is it good application?
Yeah, why is this a good application for neural nets versus just a standard off-the-shelf controller? We talked through that, right? It's a very nonlinear system, hundreds of state variables, it's got some lag in it. So that's the answer to that. All right, so here's a handout. I didn't get this posted to Blackboard, but I printed it out for you guys. This is your next project. You guys remember there's no spring break this year, right? This semester. We'll have to figure out some way to keep from fading near the end of the semester. You're fading, all right? Everybody get one? Yeah. Oh, you, okay. You got it. Thanks. All right. So this is that 2-link robot arm. And I'll need to get this posted to Blackboard so the guys on Zoom can see it. Run through that real quick because I knew I had a couple people. Give me 2 minutes, I'll go ahead and log into Blackboard and get it uploaded. Okay.
I just kept going through every single one to see if it went up or down.
I just for a while. This time.
I guess. I guess.
I think they have stuff online about it, and most of them like
We can also include it on the model.
Well, we don't have or newspaper companies to get layers. You can't do that either.
There's only like two.
Separate each thing that you test like out different ones.
Might want to touch.
Are you guys getting the yeah. That's how we can cut off the deaths of no surgery.
I did. Took me up 30 seconds. Ooh, I'm sorry. We can feed them.
All right, should be on Blackboard now. You guys on Zoom hear that? Should be on. See. So we're doing the 2-link robot arm, and the specifics, the lengths, and the height of that pedestal are shown on that sheet. And I just remember before I get into that, notice that on Wednesday we're reviewing for our first exam, and then we're going to do that next Monday. And there are 2 exams in this semester. The first one is midterm, essentially, and the next one is at the final. So the 2-link robot arms. We're trying to track the control, the position of the end effector with these angles here. We're just doing inverse control. So you just collect data. What you're going to do is put values for theta 1 and theta 2 into the robot, collect where it ends up, collect the table of data, invert it, and that's your controller to train. So it's totally up to you how you vary theta 1 and theta 2. This is U. And how many data points you collect. And it needs to operate inside this box. That's 1 meter over, and then another meter over, and then another meter up like that. So you need to figure out, well, what values of theta you're going to put in there to get points inside and around the box. So you collect that data and invert it, and then figure out what neurons you need for your networking training. And then we're going to have specific testing data sets. To see how well it does. So training and data collection, we're pretty much clear about how that works. And it will depend upon your strategy for how you vary the data here, how you vary the theta. And I guarantee you that if you include points that are way over here, way outside the region where we actually want to operate, it will make it worse. Because you're asking it to learn a much broader domain of data. All right, so the testing data set are specified there. And it's inside the box. 11 points. I say 11, all right? Yeah, along this line, and then 11 points along this line. And here, we're specifying the x2 and y2 that we want, and then the controller has to give us the thetas that then go back into the robot, and hopefully we get close to where we ask it to be. So the equations for the lines, this equation is y2 let me make sure I get the right one here. Yeah, that one is y2 is equal to 2 minus x2. Let's check it out. So we're here at 2 comma 0. That's where we want to be. We put in x equals 2, we get 0, so that's correct. We put x equals 1, we get a vertical distance of 1, check. And the equation of this line is y2 equals x2 minus 1. So if x2 is 1, we get 0. And if x2 is 2, we get 1. So that's correct. And so you just choose 11 points along that. So you vary x2 as 1, 1.1, 1.2, 1.3 after 2. You get 11 points. And so the testing data set will be structured like this. And that will go into the network. And this is for testing. And how are we going to decide whether it worked or not? Because we don't know the theta values that we actually should be at, because the controller is doing that for us. So just put some dummy values in here. And then you'll take the thetas that you actually get out of the network and you'll go into the robot. And you'll get x2, y2 in actual. And then that's what you plot to compare with where you actually want it to be. Does that make sense? So you actually run your controller, take the thetas that came out. You'll have to dummy up. You can put zeros in or whatever you want for the testing data set. It just won't have any good RMS. And then you put the thetas you get in your results file into the robot to calculate where you actually ended up. Did you follow that? So we're actually kind of hooking up the controller to the robot via the robot equations that we use. And then the other testing data set are two circles centered at 1.5, 1.5, 0.5 up, 1.5 over. And one of these is a little circle, and then another one is a big circle. And you can see why we're doing that. We want to see, well, how well does it do in the middle of the domain? How well does it do at the edges? So again, you'll generate these testing data sets in Excel or MATLAB just according to the equations I gave you. So that's real straightforward. The part that you will probably spend the most time on is figuring this out. Again, it's not hard because it's just two inputs and two outputs, and the equations are real obvious. I mean, we have the equations, it's just, you have to think, well, what kind of a strategy am I going to use to vary data when I'm big
So you drew the robot at the top of the box. Is that really where it's starting, or is it on the ground?
What do you mean?
Like without the pedestal thing. So
This here?
yeah.
Well, the inch is 1 meter, yeah.
Okay.
I just said it that way. So this is 1 meter, this thing is 1.5, this thing's 1.5, so it can reach everywhere.
Do we decide our initial conditions then, or are they set here?
This is not a time varying problem. right? So
Oh, I see.
yeah, you can choose, you just do it one shot at a time. You say 15 degrees, 45 degrees, and then it's going to end up somewhere. And then you say, okay, I'm going to try a different value of angles and see where it ends up. Yeah, it's different than the rotary robot arm because that was a time varying problem. This is just because it's easier to do this before we start varying time. This is just a good example of inverse control. Make sure you read what the normal plots, there's anything special about that. Write me a one-page description. Make sure you tell me the different things you tried as far as your network. You have to show me what strategy that you used for this, because that's a key thing you're doing. Map your network diagram, plot the training data points. I want to see what points you used in your training. In fact, you should plot that out so you can make sure that when you generated your training data set, it makes sense. If you plot it out and you get points way over here, then you know there's something wrong. And then you're going to plot the X's and the circles and turn in your network. Grade will be partially based on how few training pairs you can get away with and still get good results. I mean, it's kind of obvious that if you use 100 million data points in this square that you might get better results, although sometimes too much data is bad as well. So try to see how few training data points you can get away with and still get good results. And hidden neurons, try to reduce the number of hidden neurons when you're doing this as well.
How also do you is there like a way of finding like what is good enough? Because obviously each thing is different, each project is different than the next. How do you, I guess, or is that just a personal thing of what's a good enough error?
0. No,
Yeah.
that's your ideal. You just try to get as good as you can within the constraints of how much time we have to do this. I mean, I'm not asking you to spend the next 5 years.
Yeah, I just, because I mean, obviously you can do less points, but the errors, I mean, usually to some point the error is going to go up.
Yeah.
The fewer points. I just didn't know if there was like a
Yeah,
way
I
of
mean,
finding what's good enough of an error.
Right.
I know it's always a big question in anything.
I mean, with anything, 1% error is really good. 2%, 3%. Once you get larger than that, then you'll see that it won't hit the points very much. But when you do your results and then you plot, you'll see, yeah, if you get a circle that looks like, yeah. So I'm not going to be, I don't have some threshold where if you don't hit that, it's totally wrong. But just get it doing it the best you can. And we can't really go beyond that. I mean, if this were a robot being used for eye surgery, your error tolerance would be a lot lower, right?
Yeah.
Than if it's used for cutting wood for a sailboat.
That's what I did.
So, yeah, I'm not going to go that deep into it. But typically, you would have some kind of specs as to how accurate.
Yeah.
So I realize that leaves it a little bit open-ended. But you ought to be able to fiddle around with this and in a couple hours, get it working pretty well. All right. Well, no robot launch today, so let's call it good. I'm not robot launch, rocket launch.
That's pretty good.
Any of you guys work in the aerospace industry? Like for Spirit or Cessna?
Used to, got laid off.
Yeah, I mean, some of the latest news is that they're going to vaccinate the aerospace workers.
Oh, yeah.
So maybe you can hurry up and get jobs real quick.
Well, I mean, I think in the manufacturing sector.
Where you're in an environment where you have to be around people and you have to be there.
No. Well, thanks to the whole 737 MAX thing right before the pandemic, they were laying off crap tons of people before things.
Yeah.
On that note, Is there any way that we may be able to switch the test to Wednesday? Because I know this weekend is that block free competition.
Oh,
How many
Yes,
people
I knew
are,
about that and totally forgot about it. Are you guys participating in that?
as long as you
Well,
get
then we'll see how well you do on the test after not sleeping.
Yeah. Especially with everything.
Yeah, I forgot, I'm happy to do that. Okay, I think it's cool that people are doing that competition.
Okay, yeah.
So I'll still review on Wednesday,
That's fine, yeah.
but remind me then that we're switching it, because I'll probably forget. Okay, I know you won't forget, but.
Yeah, okay.
I don't know. Yeah, we'll keep going.
No, yeah, they don't tell you until Wednesday is when they do even.
Oh, hang on. Yeah. Hey, guys, because there's some limitations about coming to campus, I know you guys are maybe not here as much. I've put the files that you can install NeuralWorks on your home computer on Blast. And you don't really have to do an install. All you do is unzip the file and put it somewhere, and then that's your directory you run out.
So also, if you have a
Computers, I thought I was like, I
computer,
can just send this to myself.
blast, you could just copy it.
Yeah, you can do that as well.
I tried compressing it, emailing it to myself, but it will block you from that. We're saving.
Oh, on the computer, but yeah, as long as you get that internal directory and then you stick it somewhere, it doesn't really install. So, I was hoping that would help you guys out.
Sweet.
Oh, you had a question, sorry.